Okay, so let us start. So let me recall the definition, the notation for the fundamental solution. So I will use this notation here today. This is the fundamental solution for the heat equation. So it is 1 over 2 pi log 1 over norm of x minus y, etc., etc. Okay? So this is the fundamental solution defined for x different fundamental solution. The dimension here is larger or equal than 2. And we want to show the usefulness of this function by proving the following theorem. So assume that f is a continuous function, actually C2 function, with compact support in the whole space. Then, so define u for any x, then for any x, the function u of x, which is equal to phi of x minus y, f of y and y, is a solution Laplace of u equals f in Rn. Maybe it is better to write first the regularity. C2. Okay. So this is the usual convolution between, minus. So remember that this is in L1 loc. This is in L1 loc. Phi is in L1 loc. F has compact support. Therefore, we can define the convolution between F and phi. There is no problem. And then this is one solution to the to this elliptic PD in the whole space. Okay, we want to show this, and so the proof. Now maybe I can leave you as homework showing that U is C2. Well, this follows, as we have already seen something similar, I think, in the study of the heat equation. You fix a direction, a EI, a unit vector in, so this is a unit vector. And then you fix a point, and then you consider the quotient okay. And then remember that you can always write this as and then you can therefore write this quotient simply in terms of a quotient here. Okay, so the homework consists in the following. You write this quotient, writing here f of x plus h ei minus y. So this is actually is equal to the integral over Rn f x plus h ei minus y minus fx minus y by h. Now the point, now we know that f is in C2. Therefore, we know that as h goes to 0, this converges to the partial derivative with respect to xi of f, okay, at the point x minus y. And therefore, we can pass to the limit, because f has compact support of class C2, this converges to the partial derivative, we can pass to the limit under the integral sign. Okay, so this converges as h goes to 0. So this is actually homework, but just a sketch. df over dxi x minus y. Okay. Hence, there exists the limit also of this left-hand side as h goes to 0, and this limit is this. But this function on the right-hand side is continuous with respect to x, etc., etc. Okay. So this is the sketch of the proof. And so you do this also for second derivatives and so on, okay? Now, let us prove, so the regularity is okay. Now the point is to show that the PD is satisfied. Okay, so now the idea is the following. So remember that at x equal to y, we have that this is a singular point of phi, okay? So what do? We start by computing this object here at any point x. Okay, and this actually we cannot, I mean, the best is to look at the convolution in this form and to differentiate twice f. Okay? And then, so let me write it like this. Laplacian of f x minus y 5y dy. Okay. Now the idea is, of course, now well, maybe it is better to use a symbol. So this Laplacian is considered with respect to x. I am differentiating with respect to x. So this is okay. And this formula follows arguing as here. So for instance, the partial derivative from this kind of argument for homework, you see that du over dxi at x is equal to usual property of the convolution. And therefore, also the second derivative is you will prove that also the second derivative xi xj at x is equal second derivative xi xj y dy, and therefore, in particular, the Laplacian. So, from this kind of argument, it follows this and this. In particular, we will see two. Not only, but if now I take the sum over E equal to J of this expression, I obtain this. Is it okay? This implies this. Take the sum. This equality implies this. Okay, now, the point is that we would like to use integration by parts here. But we have to be very careful because phi is not differentiable, is singular at a point. In particular, phi is singular at the origin here. Therefore, it's not clear how to compute the integration by parts. So the first thing to do is to split this integral into two integrals. First, an integral out of a small ball centered at the origin. So remember that the origin now is a singularity. Now I isolate a small ball B epsilon centered at the origin of radius epsilon. So, and I write this integral as the sum of two contributes, namely these two objects here. Okay? So that here I can surely integrate by parts. So now let me follow the notation. I call this equal to I epsilon, and this equal to J epsilon maybe. No, sorry, this is I epsilon, my notation, and this is J epsilon. Okay. This is I epsilon, and this is J epsilon. Okay. Now, what about I epsilon? We can start to estimate I epsilon as follows. So in two dimension, I have that I epsilon is less than or equal than what? I have a constant here, a constant here, and then I have constant which is the L-infinity norm of this function. This is C2 of compact support, therefore this is bounded. I epsilon, yes. So this is the absolute value of this is less than or equal than a constant. Okay? And I call this constant C. Okay. Fine. Then I have the integral over B epsilon of the log of epsilon. Right, essentially. Log of y, maybe. Huh? Log of y. Is it okay?
Take the fundamental solution Take the fundamental solution
for n equal to. Yes, I'm taking the situation, the fundamental solution. This constant, maybe there is some pi, 2 pi or so. I have this L-infinity norms times 2 pi and so on. And then this is less than, say, this goes as epsilon squared, because it is two-dimensional. This goes as a log. Therefore, this goes to 0 as epsilon goes to 0. Okay. So when epsilon goes to 0, this is negligible. Okay. And when n is larger than or equal than 3, again, I have a constant, then I have epsilon to the n, which is the volume, and then I have something which is 1 over epsilon to the n minus 2, which again goes to 0. So that this is negligible as epsilon goes to 0. So let us concentrate attention on this object here. Now we can we can integrate by parts here, because now everything is smooth. Because phi is smooth, because I am outside, I'm far from the singularity. Epsilon far from the singularity. So now I can integrate by parts. And so I can write it that, so J epsilon is equal to what? So it is minus the gradient. Oh no, maybe there is another trick here. I want to integrate by parts. But if I want to integrate by parts, I need the derivative with respect to y and not with respect to x, right? But they are equal. They are equal. Because two derivatives minus times minus equal plus. Okay? So I can use this small trick so that now I can really integrate by parts. And so I have the gradient of f against the gradient of phi with the minus in front. Okay? And then I have also the boundary term dy. So I have phi of y scalar product where nu is outward. So I am integrating, I'm working on Rn minus a ball. Actually, not quite, because f has compact support. Therefore, actually, this integral is not on the wall Rn minus a ball, but is somehow here, say, if this contains the support of f, I am integrating in this annular region, right? Essentially. So, this is an open, smooth, bounded set. Therefore, I can apply the integration by parts. And therefore, this volume integral becomes a volume integral with the minus, and then there is a boundary contribution, but there is no contribution on this part of the boundary because f is 0. And the only contribution is here. And nu is exterior. Is this clear? Nu, if I put the plus here, nu is exterior to the domain. So exterior to this circular annulus on this boundary means inward with respect to the ball. Okay, so this is exterior. Okay, unit and exterior. Okay, so let me give you another notation. So let me call this, I call this k epsilon. And then let me call this L epsilon, just to follow the notation of Evans. Okay. Now, again, for the previous, arguing as in the previous case, look at this. So this is bounded because this has length 1 and this is bounded. Therefore, this is bounded. Then I have to integrate this. And again, I have, now it is worse than before, because this is length, in 2 dimensions, this is just length epsilon. But this is a log. Therefore, this again goes to 0. Epsilon, which is the length of this in 2 dimensions, epsilon times a log. Let's see in any dimension, epsilon to the n minus 1 divided by epsilon to the n minus 2, which still goes to 0. Therefore, also L epsilon goes to 0. So this goes to 0, and this goes to 0. So what really matters here is in the contribution of the integral at the end, when I will let the limit as epsilon goes to 0, what really matters is just this integral here. So let me concentrate just on k epsilon. Okay, so k epsilon. K epsilon, again, I can integrate by parts once more. So I'm using, again, just remember the usual formula. Divergence of u eta, the integral, is equal to integral of u eta scalar nu on the boundary of omega, and it is also equal to grad eta plus u divergence of eta. So I am applying this with the choice of u equal to f, so that I have grad u times grad and eta equal grad phi. So grad u times grad phi with the minus is equal to u divergence of eta, which is the Laplacian, and thank you, sorry, thank you, Rn minus the ball. And then I have the scalar product between f of x minus y, scalar product of grad phi of y mu y. Okay? Do you agree? But now there is a big advantage. I claim that this first integral is exactly equal to 0. Why is this so? This is the first volume integral is identically equal to 0. This is 0, because this is harmonic out of the origin. In particular, it's harmonic out of the ball centered at the origin. So you see, essentially we have, what we are doing here is trying to put this Laplacian here. But if we do simply this, then it happens that this is 0. And indeed, this is false. It's not true. Because we have to be careful. The point is that phi is singular. So we cannot really put this Laplacian here, and then this is 0 identically, because of the singularity. And therefore, so this is 0, but this is not 0. And this is the origin of our computation. So, pardon? Okay. So we end up with this object here. So now I keep only this. Let me work a little bit on that integral. So let me rewrite it so that I see it more clearly. So our Laplacian is equal to minus the integral over the boundary of the ball of f of x minus y, scalar product, and nu. So we have to compute explicitly the gradient of phi. So now we compute explicitly this quantity. Okay? So we do this with the constant, with the proper constant, so which now I rewrite here. So the gradient of phi with the proper constant are so phi was equal, say for instance, when n is larger than or equal to 3, was I think n minus 2 omega n 1 over y to the n minus 2. Okay? This, for instance, when in dimension larger than 2, for instance. And then this, if I take the gradient of this, then this is equal to minus 1 over omega n. Then I have here y n minus 1. And then I have the gradient of y, right? Do you agree? Huh? And therefore, this is equal to minus 1 over omega n y divided by y to the n. No, there is a mistake? There is an n missing here. Here, multiplication. This, I don't remember the constants. Maybe you're right. Huh? So check the constant, please, on the normalization constants. There is also an n times n minus 2. Okay, maybe yes. So apparently there is another n here. Okay, so it's just a matter of constants here. This is in dimension larger than or equal than 3. So that is grad phi, and nu is actually, we have said that nu is exterior to the complement. Therefore, it is equal to minus, so nu at y is equal to minus y divided by y, with the minus. Hence, if I'm not wrong, this is equal to minus boundary over b epsilon f of x minus y Then I have the constant. So minus. There is a minus n omega n, and there is another minus here. Minus and minus is plus. So I have 1 n omega n. Then there is also this minus, which I keep. Then I have the scalar product between this and this. Okay? So this is equal to y divided by y times y divided by y to the n. So this is equal to 1 over y to the n minus 1. One, okay. But y is epsilon, because I am on the boundary of the ball. Therefore, it seems to me that this is equal at the end minus 1 over n minus 1 over n omega n epsilon to the n minus 1. dHn minus 1 y. This is very nice because this is the mean value up to the sign. This is exactly the length, the area of this surface. Because this is omega n minus 1, remember? This is omega n minus 1. Therefore, this times this is exactly the area. Therefore, this is the mean value of the function, which now f is smooth. When I let epsilon goes to 0, this converges to minus f of x, the value of f at the center. Because this is simply, if you wish, this is simply minus the mean value by translation. You center it at x, so you translate the coordinates, and then you have to take the mean value, the surface mean value around x of f. When epsilon goes to 0, this converges to, since f is continuous, this converges to the value at the center, which is x. Therefore, I keep this minus, but this was plus Laplacian of u, and therefore, so we have shown that minus Laplacian of u is equal to f of x. Because this is a minus, and we started from plus Laplacian. Okay. Okay. So you see now it is very useful, this notion of fundamental solution, because, for instance, it gives us one solution of the Poisson. This is called Poisson equation in the whole space. Okay. So this shows the theorem. And now we can continue with other similar computations. So now I want to give you a representation formula. So theorem, maybe this is called third green formula. So let me remember maybe the second green formula. Please check. U Laplace of v minus v Laplace of u dy if omega is smooth and bounded, and if u and v are C2 of intersection C1 omega bar, we have this kind of formula here, u dv over d nu minus v du over d nu. So please check in your notes if the signs are correct. Pardon?
Boundary of omega. Should be
Lipschitz or omega smooth and bounded, or also Lipschitz is enough, but let me take it smooth, C1, C2, whatever, for the moment, okay? So this is maybe the second Green's identity. Just a simple application of integration by parts, usual stuff. Now we want to write, and notice that here there are no assumption on harmonicity, just valid for any u and v sufficiently smooth. No PDEs. Okay? And again, also here there are no PDEs. So, and let me take a function u, again, C2, under the same assumption on omega, C1 omega bar. Then, for any x in omega, there is a representation formula of u without assuming any PDE. Okay? And the presentation formula is the following. So I have first a volume integral that maybe I write here. Now, phi of y. No. Phi of x and y. X minus Laplace of u, y, y, plus the integral over omega of phi x minus y du over du minus u. So maybe in some books the notation is slightly different. Maybe in some books this is indicated by phi of x and y. Actually, it's a function of the difference, but we can more generally write like this. So this is also sometimes written as phi of x and y, and this is also phi of x and y. And here, what does it mean, this? This means taking the gradient of phi with respect to y, scalar product with nu. Because now the variable of integration is y. Therefore, this is the gradient of phi with respect to the variable y, scalar product nu. Okay? Okay, this is, let me check. Okay. Okay. Let me check the signs if they are correct. The plus, and the minus. So how to prove this? So notice it is interesting, this result, because there is no assumption on u. Of course, in particular, if u is harmonic, then this is 0, in particular. And say, if u is harmonic, and this is interesting because if u is smooth enough, and say, in particular, if u is smooth enough, u is harmonic in omega, say, and u is equal to g on the boundary, for instance. In particular, if I am able to prove that this has a solution, if it has a solution, then u must be equal to 0 plus this is say this is g, and this is what it is. Okay. Okay. Du over dmi. Okay. So this, of course, does not prove that this problem has a solution, but gives a representation of a solution. If you are able to prove that there is a solution, then this is a representation theorem. It's not an existence theorem, just a representation. So, but before going to this, let us prove this kind of formula. Okay, so fix x and take a usual small ball b epsilon centered at x, small enough so that this ball is contained in omega. And therefore, we can now compute, again, a similar trick as before, starting from this equality, essentially. So we integrate over omega minus b epsilon x, the Laplace of u, times phi of x and y. We compute this quantity. So let us compute this quantity here. Okay. Well, to compute this quantity, we can use this formula. So we replace, now we use this formula with the following notation. In place of omega, we take omega minus the ball. Yes, I use this notation. Okay. So in place of omega, I take this new omega. Okay? U is u, and v is phi. V is phi. X is fixed. At this moment, x is fixed, and I'm integrating with respect to y. So I apply this formula with the following: x is fixed, u is equal to u, and v of y goes to phi xy, x fixed. Everything is smooth enough because on this new omega, I am just throwing away a small ball around the singularity, which is x. And therefore, this u and this new phi are smooth enough. And omega also is smooth enough. Okay? So from that formula, I end up with the following. Integral omega minus b epsilon x of u of y Laplace of, with respect to y phi xy minus dy minus integral b epsilon x is equal to what? Is equal to u of y d over d nu phi xy minus phi xy du over d nu y plus the integral over the whole, the same quantity, u of y now, okay, nu is exterior again as before. Here this nu is okay, this nu is like this, minus phi of x and y du over d nu y dh n minus 1 y. Okay. Now, Laplace of u, Laplace of phi. I hope that the signs are correct. So let me check first what happens to this. Again, using exactly the previous arguments, arguing as before, u is smooth enough, so it is bounded, and so this goes to 0 as epsilon goes to 0, and this goes to 0 as epsilon goes to 0. Okay? Therefore, these are negligible with the exactly with the previous argument. Now, I have a minus here. Okay. I hope that the signs are correct. You see, now let me look at this. So this with the minus is this, because it's easy to see that if you compute this integrand on the small ball, again this goes to 0. So this, as epsilon goes to 0, converges to this. Is this clear? It is clear, huh? Because this is L log, this is C2. So this converges to this with the minus. Then this with the plus is this. If I put this on the right and on the left hand side, I find it with the plus. And then if I put this on the left hand side, I find it with the minus. And therefore, I just only have to show that this with the minus, so it remains to show that minus integral over omega minus b epsilon x u of y Laplace phi xy dy converges to u of x as epsilon goes to 0. Do you agree? Do you agree? So let me repeat it. I have the second Green's identity, which I apply with omega in place, with this in place of omega and this in place of v. Now, I first recognize that this contribution goes to 0 exactly for the previous reasons, because u is bounded and grad u is bounded. I integrate over epsilon, an object which goes as epsilon to the n minus 1. This goes, one shows that this times this and this times this again goes to 0. Therefore, what remains is this plus this plus this, and this again also this goes to 0. It is immediate. Therefore, this red quantity goes to this red object. Now, what remains to show is therefore that if I put this on the right-hand side, so I put this with the minus, this converges to u of x. And this is the previous computation, the computation of the previous result with the minus. Okay. Okay. So let me keep this this statement here on the blackboard. Third green formula. Okay. So now from this we want to continue the theory. So okay. So now let us slightly modify this. This will be useful for the introduction. So also let me keep the standard notation phi of x and y, sorry, so that I have it phi of x and y. Phi of x and y. And this is, so remember that this is the gradient of phi with respect to y, scalar product nu. Okay? So there is no, I mean, there is no, everything is well defined. Okay, okay, now let me work a little bit on this and assume that now h, let me call it h, C2 omega intersection C1 omega bar is harmonic in omega. Let me call this h so that we have the following. 0, I have erased unfortunately the second Green's identity. So from the second Green's identity, I have h du. We have this from the second Green's identity, right? Okay? Do you recognize it? Because, let me write it very quickly. H Laplace of u minus u Laplace of h equal h du nu minus u dh dnu. Okay? So, if Laplace of h is identical equal to 0, this is 0, and therefore h du over du minus u dh over du minus h Laplace of u is identically 0. Okay? I have this equality here. Now, I can add this to this. So let me call this formula 1. Let me call this formula 2. Okay, and let me introduce the following notation. G of x and y, phi of x and y plus h of y. So let me call capital G is this formula. And so now let us add 1 and 2 together. So let me write first so phi plus h, which is G, du over du minus u phi plus h dHn minus 1. And then I have minus G. Okay, minus G. Okay, so let me keep this information on the blackboard. And this. So this is a representation formula. And now let me make this comment. Suppose, remark. So this formula, when this formula is valid when u is sufficiently smooth, when I am able to find such an harmonic function with this regularity, and so under the omega is bounded and smooth, so under this assumption, if I define capital G like this, I have always this. Okay? Now, suppose that we can show that G of x and y is equal to 0 for any y on the boundary of omega. Assume that we are able to do this. Namely, assume that we can find h. So assume that we can determine h so that G defined is as follows, as the following property. Assume that we can do. So that assume that we can determine G so that in addition the following properties hold. Notice that x is inside and y is on the boundary. Therefore, x is inside. Y here in this equality is on the boundary. So therefore, it never happens that x is equal to y where phi is not defined. Okay? This never happens in this. Now, if I am able to determine capital G so that this is true, then I look to my representation formula. And so I have then for any x in omega, u of x is equal to the integral. Now g, here you see, y is on the boundary, and this is 0. Therefore, what remains is very interesting, because what remains is minus u of y the gradient of g with respect to y, scalar product with nu, minus g of x and y, Laplace of u, y. Okay, now you see what this is more. This now makes more precise my previous comment. Now assume that you are able to show, hence, if we are able to solve the following problem, minus Laplace of u equal to, say, f. No, sorry, u into C2 omega intersection C1 omega bar, comma, minus Laplace of u equal to f in omega, and u equal to g on the omega. If we are able to solve this, then we have a representation formula which is quite interesting, because necessarily if this is true, then necessarily u is more or not explicit, I mean, but it is representable using only the data of the problem. Namely, it is equal to minus g plus minus Laplace is equal to f and so we have proven a sort of representation theorem under several assumptions. So let me now list the assumptions. So the main assumptions are, so let me now, okay, so do you agree with this? You see now that on the right-hand side, there is not u anymore. There is not u, because this is f and is given. This is g, which is given. And then, of course, there is this function, capital G, which is very difficult to find, usually. So which are the assumptions? So the assumptions are existence of this problem, essentially, with this regularity. We always want this regularity because we always use the second Green's identity. And the second Green's identity, you need the derivative of u on the boundary. And therefore, it is better to have u C1 up to the boundary. Okay. Next, we also are supposing that we can determine capital G so that this following property holds. So under all of these assumptions, we have somehow implicit representation of the function, of the solution of a Poisson equation of this sort. Okay? Yes?
Suppose that we can solve capital D.
We can find capital G, yes.
And we show that this, by defining U, that this expression solves this solution.
Yes. Yes, at the end, yes.
So this means that we solve this.
This is actually, exactly, this is a good comment. I mean, this is not an existence theorem, it's just a representation, but it suggests you how to prove existence. Because then you try this, assume that you have G, then you try to prove that this actually is a solution. And indeed, this is what we do usually. It is also, this suggests also how to prove existence. Okay, maybe now I keep this.
How can we find the
This is very, very difficult usually.
something like geometry?
Yes, it has. Now let me. Yes, how to find G usually depends on omega. It depends on omega, and so for particularly simple omega, it is possible to find explicit G. For omega generic is usually not. So, so now let me give you a definition. Definition. So let fix x in omega. A Green's function g of x and y, Green's function for the operator Laplacian on omega, is a function of the form g of x and y equal phi of x and y plus x is fixed now. So if I consider x is fixed, now I look at h as a function of y, where phi is the fundamental solution of the Laplacian. And h maybe this is enough. H is such that it is better to give a formal definition to what we have deduced up to now. So this is the famous Green's function for omega. So now, as he has observed just 5 minutes ago, essentially, the problem of solving minus Laplace of u equal to f on bounded domain omega or on some domain omega, u equal to g on the boundary, is essentially reduced to find the Green's function. Okay? Okay, maybe homework. Home. If G exists, then G is unique. It is unique. Try to show this. Use the maximum principle. Because you have to show essentially that this H is unique. But this H satisfies a PD because it is harmonic and on the boundary has a suitable phi. So this is almost immediate, right? I mean, H is unique because the Laplace of H is equal to 0, and on the boundary this plus this is equal to 0, and therefore this on the boundary is minus this. This is the proof. Okay. So I would like also to rewrite once more what we have shown up to now, theorem. Let omega be open, smooth, bounded. Suppose that maybe sometimes in the book the Green's function is denoted also by G of omega, maybe sometimes. Okay, just to remember that depends on omega. Suppose that there exists the Green function for delta on omega. Then, if U is a solution, if U solves U into C2 minus Laplace of U equal to F, U equal to G, then okay, so now we want to make an example for this. And we want to find the Green's function for the sphere. So do you agree for this statement? So there are a lot of assumptions, it is clear. Regularity assumptions, the existence of the Green's function, which is usually a difficult problem, and the existence of this regular enough up to the boundary also is non-trivial, and so on. Of course, say that G and F here are continuous, J and so that everything is well defined. F and G are continuous. So this is the main theorem of today. And now it is important to make at least one example of the computation of the Green's function. Okay? So there will be no time to conclude this example today. So we just start, and then we continue tomorrow. So here, everything is strictly related to potential theory in physics. So the fundamental solution is the potential generated by a pointwise charged particle at the point x. That is the electrostatic potential generated by this, which is singular at x, of course. And so if you have studied electromagnetism, the electric field, the magnetic field, you surely recognize a lot of analogies between this and the potential theory. Okay, U is sort of potential generated by a distribution of charges. So now let us take as omega the ball of radius r. Okay. Now let us do the computation just only in dimension n larger or equal than 3. Okay. So now take a point x in omega and define the following new point, x star. X star actually is a new point depending on x, okay, which is along the direction okay. Now home, check that x star is outside omega. So if x is inside, this point is outside. Sort of specular point. Now we will see in which sense it is specular. Home, 1, 2, x therefore, you see, if this is closed, x is not the origin. Okay? So take a point which is not the origin. From this relation, you see also that, so take this point, now I will make a picture. If x is very close to the origin, so this is very small, then this must be very large, because the product must be constant. Sort of inverse. Now let me try. I try to do a sort of picture. Okay. So this is BR. Then I have a point x here. This is the origin. And this point, say, is x star. You see, x star is in this along x, same direction, but with a different length, depending on x. Okay, sort of. Okay. Fine. Now, we look for g omega of the form of the following form. Okay, there is a singular part here, which is the phi of x and y. And then we look for some, now we look we look for G, a special form, fundamental solution, minus some constant to be determined, fundamental solution, however, here there is X star. Okay. Alpha to be determined, and alpha must be determined so that alpha to be determined so that the boundary of the ball. Okay. Okay. So now, home, so that tomorrow we can be more quick. So take a point y here. So take a point y on the boundary of S, of the ball. And consider the following triangles. So the triangle I'm considering are O, Y, X star, and the other triangle is O, Y, and X. Y is a point on the boundary of omega. Once you have X star defined as here, sort of specular point of X with respect to the boundary. See?
If y lie in the same line.
Yes, also you can do. But generically take this situation. Okay. So, okay, assume that y is not this, okay? Take all the other y's. Now, check that these two triangles have same angles. Check this, that these two triangles have the same angles. Of course, you have to use this definition of X star. So they are similar. These triangles have the same angles. Of course, they have an angle which is common to both. But then I claim also that the two adjacent edges to this angle are proportional. So try to check this, so that they have one angle and the two adjacent sides of each triangle are proportional, then they have the same angles. Okay? Namely, this is equal to this. Okay? So check this, and tomorrow we will compute. Now maybe I can anticipate for you what is the green function at the end for the sphere. Maybe you can try to do by yourself. It's not easy. It's not easy. But the green function for the disk, for the sphere, has the following expression: 1 n minus 2 omega n, 1 divided x minus y n minus 2 minus okay. So this is much more difficult. Try to show also, so these 2, 3, and 4.